Let's start. Hi, everyone. My name is Rohit Agarwal. I'm a software engineer at Google. I work in the Kubernetes engine team, which is part of Google Cloud. And today I'm going to talk about using GPUs with Kubernetes. Before we begin, a quick show of hands. How many of you are already using GPUs on Kubernetes? Awesome. And how many of you are using GPUs that are not NVIDIA GPUs? There's maybe a one single person. Okay. Yeah. Okay. So in this talk, I'm not going to talk about why to use GPUs or when to use GPUs. I'm only going to focus on how to use GPUs on Kubernetes. I'll start by talking about what makes it hard to use GPUs from containers. I'll go into a bit of history about the GPU support in Kubernetes. And then I'll talk about what you need to do as a user and as an operator to get GPUs working on Kubernetes. And finally, I'll end with describing what's missing and where the support is going next. OK, so containers and GPUs. One of the things which make containers great and have made them so popular is that you can package your application and all of its dependencies in a container image, and then you don't have to worry about missing dependencies or conflicts with the other applications. You can run that container image anywhere. However, this property breaks down when one of your application dependencies is a kernel module. Containers use the host kernel. So if one of your application dependencies is a kernel module, then the host on which your application container is supposed to run needs to have that kernel module installed. And applications using NVIDIA GPUs are examples of such applications. Using NVIDIA GPUs require the NVIDIA kernel module to be installed on the host. Using NVIDIA GPUs also require the presence of NVIDIA's shared user-level libraries to be accessible from inside the container. These libraries are used to communicate with the kernel module and therefore the GPU devices. So you need the libraries, you need the kernel module on the host, and you need the libraries to be accessible from within inside the container. So maybe you can package the libraries in the container image and assume that the kernel module will be present on the host. Except the version of the NVIDIA shared libraries needs to be the same as the version of the NVIDIA kernel module. So if you package these libraries in your container image, then your container image is no longer portable, because it depends on the version of the kernel module on the host. So if you package it for a particular version, it will only run on hosts which have the kernel module of that version, right? So this is not good. You don't want to make your container images non-portable, because that defeats one of the main advantages of containers. So in Kubernetes, the first thing we decided to do to support GPUs was very simple. We decided to let the user deal with these dependencies. All Kubernetes would do is that it would assume that the NVIDIA driver is already present on the host, and then it would see the GPU devices present on the host and expose them as schedulable alpha.kubernetes.io/NVIDIA GPU resources. And when a container asks for this resource in its resource requirement, then Kubernetes would add these devices to the container. So this is all it would do. It would keep track of the GPU devices on the host and attach them to the container when requested. So now you have devices attached to the container. How do you access the device from inside the container? So as I said before, to access the device, you need those user-level libraries. But also, if you have those user-level libraries, then your container image is not portable. So we recommended the users to install both the kernel module and the shared libraries on the host, and then use host path volumes to inject these libraries inside the container. So install both them and the host, create a host path volume, inject that volume into the container. So this is how it looked like. In blue, you see that this pod or this container is requesting 2 GPUs, and this is the same place where you'd add CPU and memory. At the top right and red color, you see that we are creating a host path volume called NVIDIA libraries, and the path there is the path on the host where these shared libraries are present. And at the bottom in red, you see that we are adding this host path volume called NVIDIA libraries inside the container at a mount path. And this path in the container needs to be a path which is in the shared library search path. So after you do this, your container image will be portable, and things will work. But this is still terrible because your container image is portable, but your pod spec is no longer portable. Your pod spec contains some host-specific stuff, and we don't want the pod spec to be not portable. So there were some other things which were undesirable about this approach. So this support for NVIDIA GPUs was in tree. It was part of Kubernetes core code base. And that's not ideal, because what happens when other vendors want support for their devices in Kubernetes, right? We cannot continue expanding the Kubernetes code base to support all these things, right? We cannot add AMD GPUs, Intel GPUs, Xilinx FPGAs, and so on. At the same time, we also cannot play favorites to a particular vendor, because Kubernetes is the open source software and supposed to work well with everything. As a result of these things, we deprecated the in-tree support in 1.10, and in 1.11 we are completely removing the in-tree support. So this resource will stop working in 1.11 completely. To replace this in-tree support, we added device plugins in Kubernetes. Device plugins are a way to support generic devices in Kubernetes. It's an extension mechanism which allows the vendor-specific code to remain outside the core Kubernetes tree, but still allows these devices to be available natively through the Kubernetes API. And they also enable the pod spec to be portable. The pods, if you use device plugins, the pod spec will not contain any host-specific parts which we had in the previous pod spec. So this is how it looks like now. In blue, you see nvidia.com/GPU. So all you need to do now is add the resource exposed by the device plugin in your resource requirements. For NVIDIA GPUs, that's nvidia.com/GPU. And once you do that, everything will work for you. You'll notice that there's no host-specific part in this pod spec, right? But now, where is the magic? There's no host-specific part in the pod spec. How is the container getting access to the shared libraries present on the host? And the magic is in the device plugin APIs. Device plugin APIs allows the device plugin to set environment variables inside the container or mount volumes inside the container. So for example, the cluster administrator could configure the device plugin to point to the path on the host where the shared libraries are present. And when the device plugin sees a pod requesting GPUs, it will add that volume to the container so that the container can access this, right? So with this, you have your container image, which is portable because you don't have user-level shared libraries in the container image. And your pod spec is also portable because you And your pod spec is also portable because you don't have any host-specific stuff in the pod spec. All the host-specific stuff is part of the device plugin, which is configured by the cluster administrator who knows about the host. So device plugins were introduced as an alpha feature in 1.8. They went beta in 1.10, and if you're using GPUs with Kubernetes, you should start using device plugins. So just to recap, what do you need to do as a user? As a user, you should build your images without user-level shared NVIDIA libraries like lib, NVIDIA, ML, .so, and so on. They should not be part of your container image. However, the container image should still contain the CUDA toolkit. So the CUDA toolkit does have some dependence on the host driver version. So for example, each CUDA version requires a minimum driver version, but this dependence is not as onerous as the one with shared libraries where you have to match with the exact kernel version. So you build your container image with the CUDA toolkit, but without the user level shared libraries. And then all you do is request nvidia.com/GPU in as part of your resource requirements. And if the cluster administrator has set up the cluster correctly, then everything should work for you as the user. There's maybe one more thing you may have to do as a user. So let's say your cluster has multiple types of GPU nodes. So for example, some GPU nodes have Tesla P100 and some GPU nodes have Tesla V100. So there is, and you want your application to run on a particular type of GPU. So you want to say that I want my application to run on nodes which have V100. So there's unfortunately no native way of doing this targeting in Kubernetes. Kubernetes does not natively understand different types of GPUs. It only understands that you're requesting a GPU. It doesn't understand that you're requesting a V100 GPU, etc. As a workaround, what you can do is you can ask your cluster administrator to label GPU nodes with the type of GPUs that are present on the node. So you can ask your operator to label the P100 nodes with P100, V100 nodes with V100, and so on. So this is, for example, what we do in GKE, where you can say that I want this pod to run on a node which has Tesla K80s. And then this pod will schedule on a node which has Tesla K80s. OK, so we learn about what we need to do as a user. What do you need to do as a cluster operator to create a functioning GPU cluster? So first of all, you need to have nodes with GPUs. These things are very expensive. And as I said before, if you have multiple types of GPU nodes, you should label them so that your users can target a particular type of GPU. Then, and this is one of the most important things, need to install the NVIDIA driver. And I can talk about just this point alone for a long time, unfortunately. But I'll just keep it short here. So few things which we need to keep in mind about this. Parts of the NVIDIA driver are closed source, and Linux is GPL licensed. So keep that in mind. And the other thing you'd want to do is you'd want to keep up with the driver version required by the latest CUDA release. So as I said before, CUDA toolkit has some dependence on the driver version. So you'd want that if CUDA releases a new version, that you update to a driver which is required by that version. And if you because what would happen eventually is that your users will start using newer CUDA versions. And if you have not updated the drivers on your nodes, those containers will stop running because CUDA 9.2 requires, I don't know, 395 dot something driver, which your nodes don't have. In GKE, we use a daemon set to install the drivers. You can look at that and fork that and do your own thing. You'll also need to install the device plugin. There is a device plugin for NVIDIA GPUs available from NVIDIA. There's one available from Google. You can choose whichever one fits your needs. I'm hopeful that in the future we'll converge them so that you get the best of both worlds. But right now there are two different device plugins, and you can use whichever one you want. OK, so now you have a cluster with GPUs running. What else you may want to do? One of the things you may want to do is you may want to set up resource quotas per namespace. You may want to say that my marketing namespace or my production namespace can only use so many GPUs. So we added support for doing that in version 1.10. And this is how it looks like. In purple, I think, you have what this is saying that whenever this object is created in a particular namespace, the total number of GPUs that can be used by different pods or single pod in that namespace is 4. So you can set limits like that per namespace using resource quotas. Um, we also have, so one of the other things which your users may want you after you have a GPU cluster is for GPU metrics for their workloads. So Kubernetes already supports a couple of important metrics which users care about for their workloads. So these are memory usage and GPU duty cycle. Uh, they are collected by C-Advisor, which is a monitoring agent which is built into the kubelet. And they're collected using NVML, which is a closed source NVIDIA's management library, which can be used to collect GPU metrics. And these metrics can be accessed using C-Advisor's Prometheus endpoint or Heapster or Google Stackdriver. And they were added in 1.9, so you can already use them. This is one other very interesting thing which a lot of you should do if you are not doing it already, is that you want to, because GPUs are expensive, you want to create dedicated nodes for GPU workloads. And why do you want to do this, right? So you want to prevent pods that are not requesting GPUs from getting scheduled on nodes which have GPUs. This helps to make sure that when a pod which is actually requesting GPU arrives, there's some place to schedule it. Because if that GPU node is already busy running non-GPU workloads, then you will get into a situation where your GPUs are idle and your pods requesting GPUs are pending. And you don't want to be in that situation because that's just wasting money. Another thing this helps with is to aggressively downscale nodes if you are in a cloud environment. So if let's say you don't have any GPU workloads at the moment, your machine learning scientists are away on vacation or whatever, and if you prevent pods that are not requesting GPUs from scheduling on GPU nodes, then those GPU nodes will be empty when there is no GPU workload. And the cluster autoscaler can scale those nodes down and save you costs. And how do you do this? The way to do this in Kubernetes is to add taints to node. So what you do is you would taint the GPU nodes with some taint, and then no pod will schedule on them until it has a corresponding toleration. So you'd add those tolerations to the pods requesting GPUs. So what will happen is now you have nodes with GPUs that have taints. Someone submits a pod that does not request GPU. It doesn't have that toleration. It doesn't get scheduled on a GPU node. Someone submits a pod with GPUs, adds that toleration, so it gets scheduled on that node, right? In 1.9, we added an admission controller called extended resource toleration. So this controller recommends that you add a particular taint to your GPU nodes. So it tells you what the key of that taint should be. And if you do that, what this admission controller will do is that it will automatically add a toleration to your GPU pods. And so what you do is you add the taint suggested by this admission controller to your nodes. This admission controller will automatically add tolerations for that taint in pods that are requesting GPUs. And so those pods will get automatically scheduled. Right? So you wouldn't have, your users would not have to worry about that I need to add tolerations to my pod spec. That will happen automatically for them. So the pod specs will remain, they will not know that there is a dedicated GPU node pool or something. They'll just submit the GPU workloads. Only the workloads which request GPUs will schedule on those nodes, and nothing else will schedule on those nodes. Okay, so we talked about what is already present in Kubernetes for GPUs. What's missing? So there is no support for GPU in Minikube. A lot of people have expressed interest in this. A lot of people have asked about it, but the development of this is not done yet. And this is a great area where people can contribute. There's also no fine-grained quota control. Now, what do I mean by that? I mentioned that you can use resource quotas to cap the number of GPUs that can be used in a particular namespace. But because Kubernetes does not natively understand the types of GPUs, it only understands whether something is a GPU or not. We cannot say that in this namespace I want to only allow 4 K80 GPUs or 4 P100 GPUs. You can only say that I want to only allow 4 GPUs, right? So there's no fine-grained quota control, and there is some design discussion going on how to support this. And as I said, there's some user level metrics already present in Kubernetes for GPUs, but more metrics can be added. Specifically, a lot of metrics which are required by cluster administrators. For example, they may want GPU temperature or power usage, etc. They are not present at the moment. And we are working, like we're designing how to add these metrics without polluting the Kubernetes core and like having an extensible way of adding these metrics. There's also no support for GPU sharing. So when a GPU is attached to a pod or a container, it's exclusively used by that container. No other container can use that GPU at the same time. Also, you cannot request half a GPU. Like you get the whole GPU or you get nothing. So there's no GPU sharing, it's exclusive usage right now. And we are thinking about how to do this, and like there's just thoughts right now, I think. Kubernetes is also not aware of GPU topology. So if, for example, you get scheduled in a way that the topology is wrong, you may not get the performance you want with your workloads. So this is another thing which we are actively thinking about, but there's no concrete design or anything yet. Finally, the auto-scaling support in Kubernetes for GPUs is not ideal. So there is auto-scaling support. You can auto-scale based on the number of GPUs, and if there are pods pending, the autoscaler will know, oh, these GPU pods are pending, so I need to add nodes with GPUs. But it's not ideal. And the reason for this is, again, the same. Kubernetes is aware of GPUs. It's not aware of GPU types, right? So pod is pending. It requires 2 GPUs. What type of GPU node should I add? Should I add a K80 node or should I add a P100 node? And there's some hacks in the autoscaler which work with us, but like that's not an ideal scenario. And we are again working towards fixing this situation. Okay, so I have a shameless plug now. If you don't want to do all of this, you can run these 2 commands in GKE, and you will have a GPU cluster working. The first command creates the GPU cluster, and the second command installs the driver. Yeah, you still have to install the driver. Any questions? Yes, sir. So the question is, what if there are multiple types of GPUs on the same node? Yeah, so we have not heard a lot of use cases, and I'm not sure if there are any plans to immediately support this. I'm hopeful that the design we come for, where we make GPUs or we make Kubernetes or device plugins aware of GPU types, may handle that use case, but like that's not a very common use case. People usually have heterogeneous clusters. Heterogeneous nodes are not that common. So, yes, sir.
My question is about CUDA interoperability with the latest, different versions of CUDA with the latest drivers that you recommend to install. Have there been cases where there was no backwards compatibility, so you had to use an earlier version of the driver for an earlier version of CUDA? Or is the latest driver
Yeah.
good?
So the question is, has there been cases where newer versions of CUDA don't work, or older versions of CUDA don't work on newer versions of driver? I have not seen them. Like, thankfully, CUDA versions have been backward compatible. Like, the drivers have been backward compatible with the old CUDA versions. So that has been very nice. Yes. Yeah.
Like collecting that information, possibly just billing purposes, or just knowing how much work the task is.
Yeah. So the question is, what about power metrics for workloads? Yeah. So we are working on making sure that we can add more metrics, uh, or we're working on making sure that we can add a way to extensively add more metrics to Kubernetes workloads. But I think that will happen maybe in 1.3. Like we're hopeful for design in 1.12 and then some implementation in 1.3. Yes.
One more question. Is there a recommendation for the base image from which to build your containers? Because NVIDIA provides some images and there are other ways. So
Yeah.
what's the best?
Yeah. So the question is there a recommendation for a base container image to build your containers on? We recommend NVIDIA's CUDA images, which are available on Docker Hub and on GitLab, I think. Yeah. So they work pretty well. I think in the back.
Yeah, you are not at all touched on the NVIDIA runtime environment. And when I was setting this up a couple of months back, I was forced to use the NVIDIA runtime environment for Docker. Now you say we are just installing the drivers. So how does the NVIDIA runtime environment fit into?
Yeah, the question is, how does the NVIDIA runtime environment fit into all this? So for NVIDIA container runtime, you still need the driver installed. I think there is some talks about how to integrate both of them together. But right now, you still need the driver installed for NVIDIA container runtime to work. And you so as I mentioned, there are two device plugins right now. The NVIDIA's device plugin uses NVIDIA container runtime underneath to make the shared libraries available to the container. The Google one doesn't do that yet, but yeah, so that's how it fits. Like it's a way of getting these shared libraries available to the container. It does some other things as well, but
But right now, I'm telling my nodes to use the NVIDIA runtime environment when they start up the Docker daemon for that node. Is that necessary? Or
uh,
you make it work for only those kind of containers that needs the NVIDIA runtime environment?
is the question that whether you can use GPUs without the NVIDIA container runtime?
No, it's just I'm not sure I understand the mapping between the NVIDIA runtime environment and the Docker daemon itself and the driver.
I see.
Who is what when?
I see. So the question is, what is the relationship between the Docker daemon, the NVIDIA container runtime, and the driver? Right. So the Docker daemon allows you to have multiple container runtimes. Right. By default, you use runc. NVIDIA container runtime is runc plus a pre-start hook, which adds some things which make your shared libraries available and so on. So the Docker daemon is like Kubernetes does not actually require Docker anymore, right? There is a CRI API which can talk to CRI-O, which can talk to multiple container runtimes. So Docker is basically talking to the container runtime underneath to start the container. NVIDIA container runtime is just one of those runtimes. And it's very close to runc, which is the default runtime in Docker and in CRI-O and in Kubernetes. And the driver is totally separate. Driver is basically a collection of the kernel module, the shared libraries, and some debug utilities. So you need to install the driver, which will install these things. The NVIDIA container runtime, after that, will make these shared libraries available in the container. And Docker is just one way to use the NVIDIA container runtime. You can use Kubernetes directly, and you can use CRI-O as well. Yeah. Yes.
About this, what's missing is what things that are being activated in Quota, also distributed type of arrival for some of these.
Oh, so the question is, what are the estimated time when the things which are missing arrive? It's really hard to say. It's like software estimation, right? But so the monitoring thing is one of the top priorities of the resource management work group, which works on device plugins. The GPU sharing and GPU topology is in very early design phase. And then Minikube is like, we're just looking for someone to add Minikube support. Like it should. So Minikube support is, you can add it on Linux, you can add it on Mac. The Linux one should be fairly easy because Minikube on Linux can run with a mode called driver equal to none, not the NVIDIA driver, but the VM driver, and that should be fairly easy. But no one has just gotten around to do it. On Mac, I'm not sure. I think it'd be a hard thing on Mac or Windows. Maybe on Windows it'd be easier. And what else was there? I forgot. But yeah, like this, all of them are, yeah. So the other things were making the autoscaler better and making finer grained quota control. That's also in the design phase. So hopefully in 1.12 you'll start seeing some sorts of like some, at least some design in 1.12 for all these things, and hopefully later you'll have some alphas and betas. Yes, sir.
Do you have anything to say about the use of device plugins for things other than CPUs, such as FPGAs or network cards?
Yeah, so people have used device plugins, I think, to implement like provide an FPGA device, but I am not very familiar with that. Like there are examples out there, and so there is you should look up resource management work group where we talk about these things, and like you can talk to more people there, and they'll have more insights about this. Okay. All right. Thanks a lot, everyone.